Lesson 6-9, the second law of thermodynamics and heat engines. So the second law of thermodynamics deals with spontaneous processes. And the spontaneous processes is that heat moves from high to low temperatures. High temperature to low temperature. Heat goes spontaneously, so naturally, from a high temperature to low temperature, until it's all the same temperature. A heat engine uses part of the spontaneous heat transfer to do work. So our work is the heat in the hot area minus the heat in the cold area. So we use this heat transfer to do work. The efficiency of the heat engine is the amount of work you get divided by the heat in the hot area. Well, the work is the change in heat over heat in the hot area. That becomes 1 minus QC over QH, the cold heat over the heat in the cold area over the heat in the hot area. And so this is only 100% efficient, meaning the efficiency is 1, if no heat goes into the environment. So in other words, the heat in the cold area is the environment usually. So if the heat that goes, and that kind of makes sense, right? It's 100% efficient if all the heat becomes work and we have no heat going to another area. All right, so there are several different ways to state the second law of thermodynamics. And for heat engines, it's the Carnot engine operating between two given temperatures has the greatest possible efficiency of any heat energy operating between these two temperatures. And you're going to say, well, what's a Carnot engine? Well, just a minute. Furthermore, all engines employing only reversible processes have the same maximum efficiency when operating between the same given temperatures. So a Carnot engine is only reversible processes. Well, remember, nothing's completely reversible because heat is always lost to the environment. But we're talking about ideals here. And so if that's the case, our efficiency can be talked about in terms of temperatures instead of heat. So a Carnot engine uses only reversible processes. So here's an example of the graph anyway. So we start at point A. We have an isothermal process. And in an isothermal process, the temperature doesn't change, so the heat that comes in is turned directly into work. All right, so the heat comes in, and then from B to C, the adiabatic expansion, the heat makes the volume increase. And then we have from C to D an isothermic process, which decreases the volume, and some heat goes out into the environment. And then last we have an adiabatic compression, so no heat exchange, but the volume decreases a little bit, but the pressure increases greatly, and we're back to where we began. The amount of work is the shaded area in the middle. So if you make that shaded area as big as possible is what we'd like, so we have most work. You're going to say, but I still don't know what a heat engine is. Well, a heat engine is pretty much anything that uses heat to make it run. And so, for example, your car engine. a steam engine. All right, so your car engine, you have the spark plugs, it ignites, heat causes the piston to move down, it does work. Piston goes back up, pushes whatever gases, the exhaust out, starts over again. That's a heat engine. Steam engine is very similar. Steam comes in, expands, pushes a piston, and then the piston will then come back, push the now cooler steam out, and the new steam will come in and it goes back around. Here's another type. This is a heat pump. Heat pump uses the Carnot cycle to move heat from a low temperature to a higher temperature. So it's actually making the heat go backwards. That's why it's called a heat pump, but it's using the same idea as a heat engine. All right, so we start here at the condenser. The gas, the high temperature and pressure in the condenser. So it's a high temperature in the condenser, so it naturally flows into the room. And then it goes up and around, we hit the expansion valve. So it's really just lets the gas expand. So as the gas expands, it lowers the temperature and the gas turns into a liquid. The liquid then flows around to the evaporator. So this liquid's really cold. In fact, this liquid is colder than the area we want to cool. So since it's colder than the area we want to cool, heat flows from the cool area into the colder liquid. So now our liquid's a little bit warmer and it goes to the compressor, which uses energy to compress that, increasing the pressure and the temperature, which gets back to the condenser, and we start the cycle over again. The heat pump coefficient of performance is how they're rated, and that's the heat in the hot area over the work. And notice that's 1 over the efficiency. So the coefficient of performance is the reciprocal of the efficiency. So a low efficiency means a high coefficient of performance. For a Carnot engine, the efficiency was 1 minus the cold temperature over the hot temperature. So the lowest efficiency is when the two temperatures are essentially the same, which means the heat pump will work best when there is a small temperature difference, which kind of makes sense. Your air conditioner is a heat pump. It'll work the easiest when the inside and outside temperatures are essentially the same. It has to work much harder when it's very hot outside and cool inside. An automobile engine, which is a heat pump, or is not a heat pump, a heat engine, has an efficiency of 20% and produces an average of 23,000 joules of mechanical work per second during operation. Part A, how much heat input is required? Well, efficiency for a heat engine is work over the hot energy. So our efficiency is 20%, and our work that we're getting out is 23,000 joules, and we have that heat. So multiply by the Q, divide by the 0.2, and we get our heat then to be 1.15 times 10 to the 5th joules. So it is taking that much heat to make this engine run. Part B, how much heat is discharged as waste from this engine in per second? All right, so our efficiency is also 1 minus QC over QH. All right, well, I know the QH and I know our efficiency, so our efficiency is 0.2. I'm looking for the discharge going into the environment, the cooler heat. So the hot area, heat going into the hot area, or from the hot area, is that. So I'd probably subtract the 1 first. So that'll give me negative 0.80. Then I'd multiply it by the negative 1.15 and get the QC to be 92000 joules. All right. The heat coming in was the work was per second, so we could say this is also the heat going out per second. So 92 kilowatts of waste. It's just a lot of waste. There's a lot of waste in an automobile engine. Refrigerators and air conditioners are similar to a heat pump, but designed to cool. And so, since they're designed to cool, the coefficient of performance for a refrigerator is the cool heat over the work. Since the heat from the hot area equals the heat from the cool area plus work, that is the coefficient of performance for the heat pump minus 1. So a heat pump has a coefficient of performance of 3 and is rated to do 1500 watts of work. How much heat can it add to a room per second? Well, our coefficient of performance for a heat pump is the heat from the going into the hot area, or heat from the hot area over the work. Every second, our work is 1500 joules. So power is work over time. So if we talk about just 1 second, we can work this out. So our work is 1500 joules in 1 second. Therefore, our heat must be 4500 joules, or the rate would be 4500 watts if we want to talk about per second. Part B, if the heat pump were turned around to act as an air conditioner in the summer, which some of them do, what would you expect the coefficient of performance to be? Well, the coefficient of performance for a refrigerator is the coefficient of performance for a heat pump minus 1. So that would be 3.0 minus 1, which is 2.0. Pump out some work about heat. Have a good day.